Hello, guys. Welcome to the post contest discussion of Codeforces Round 967, brought to you by TLE Eliminators. So, interesting fact, I was recording this post contest discussion and I came up with some very beautiful solutions for some problem. So, it's going to be very amazing. We'll be discussing problems A, B, C, and D. So let's not waste any time. Let's get started. Okay, guys. So let's start with problem A. You are given an cyclic array A1, A2 up till AN. You can perform the following operation on A at most n minus 1 times. Let M be the current size of A. You can choose any two adjacent elements where the previous one is no greater than the latter one. What this means is that you select an integer I such that AI is smaller than equal to A plus 1 mod M and delete exactly either AI or AI mod M plus 1. Our goal is to find the minimum number of operations needed to make all elements in A equal, right? So guys, what does the problem say? Let's have a look. So we are given an array, okay, of n integers. In each operation, we select an I such that AI smaller than equal to AI plus 1 mod n or mod m, where m is the length of the array. Let's say we chose this I, so this will be the next I plus 1 because it's a cyclic array. Okay. Then we have to delete, okay, either this element or this element, right? This is one operation, right? Now, what is our goal, guys? Our goal is to do the minimum number of operations, okay? Minimum number of operations such that all elements become equal. All elements become equal. Okay. Now, guys, first thing we need to notice some things for people who weren't able to solve this question. Is it always possible? Is a question that will come up in our mind, right? Is it always possible to make the array into one element? Let's consider the case 5, 1. In this case, I cannot select this as I because the next element is smaller, right? If it was 5, 5, it would not have been an issue. If it was 5, 6, this would still not have been an issue. But in 5, 1, it is indeed an issue, right? But guys, I can select I as the last element and then 5 becomes the next element and then it becomes valid. Okay. Now let's take a random array 1, 2, 5, 3, 7, 7, 6. Now let's check for each number if it is possible to make it the last element standing in the array. And let's see how many operations it takes, right? Let's do that. So for 1, 2, 5, 3, 7, and 6, let's see how many operations it does take. Okay. So for 1, it is very simple. It's the smallest element in the array. So I can just keep selecting numbers and delete those numbers. And then 1 becomes the last number standing. It took me 6 moves because there are 6 other numbers apart from 1. Okay. Now let's see for 2. Now guys, I can select these two numbers and now I'm not compelled to delete 2, right? I can delete 1 as well. And once I am done deleting 1, you can see that all elements on the right are greater than 2. So I can just do the same operation, and again in 6 moves, I can delete every other element. Similarly, for 5, I can use a similar strategy. On the left hand side, I can choose these elements and delete them. Now the interesting part is, how will we delete everything on the right? Now to delete everything on the right, this is very simple. I will choose these two elements and then delete this. I will choose these two elements, then delete this. And then I will choose these two elements and then delete 3. So the array remaining is only 5 and 6. Then I will choose these two and delete 6. So you can see that it is indeed possible to make 5 the last element standing. And how many moves did it take? Took me again 6 moves. Now for 3 also the answer is 6. You can verify for yourself. Now for 7. Guys, I don't need to delete 7 elements. I can just 6 elements. I can just delete 5. Okay. And how to do that? Of course, since 7 is the largest element in the array, I can just select these elements along with 7 and delete them. And finally, to delete 6, I will select 6 and then the first element of the array in the end, which is 7, delete it. And then it took me 5 operations. For 6, again, it will take me 6 operations, right? So what is the basic observation here, guys? That the number of operations is just n minus count of x, right? How many times does that number occur in the array? Minus n minus count of the occurrences of the array. Since 7 comes 2 times and the size of this array is 7, so 7 minus 2 is equal to 5, which is indeed the number of operations required to make all elements equal to 5. Since we need minimum number of operations, we need this number to be as small as possible. Hence, we need count x to be as large as possible. Hence our answer, we just need to find the number which is most frequent in our array, or basically frequency, highest frequency of the array. And after we find that, I can just print n minus count of highest frequency, right? That is all that I need to do. For example, let me take some cases 1, 2, 2, 2. In this case, the answer is 4 minus 3. If I take 1, 2, 1, 2, 1, here it is 5 minus 3, right? Because 1 is the most frequent, 2 is the most frequent, and their frequency are 3 respectively. Okay, so that is more or less for this problem. Let me show you the solution for this problem. It is just a greedy strategy. In a map, I am storing the frequency of elements, and in this variable called frequency, I am storing the maximum frequency of the array. In the end, I just print n minus frequency. A very simple and straightforward problem. Okay, guys, now let's move on to problem B. Problem B is actually very confusing for beginners. It was also confusing for me, but today we'll be decoding this problem very efficiently. Okay. There is an integer sequence A of length n, where each element is initially -1. Misuki has two typewriters where the first one writes letters from left to right with a pointer initially pointing to 1, and others write letters from right to left with a pointer initially pointing to n. Misuki would choose one of the typewriters and use it to perform the following operations until A becomes a permutation of 1 to n. Write number. Write the minimum positive integer that it isn't present in the array to make element AI, right? Where I is the position where the pointer points at. Okay. Similarly, carriage return. Return the pointer to its initial position. And last but not least, move pointer, which moves the pointer to its next position. What is our task, guys? Our task is to find such a permutation such that minimum number of carriage return operations needed to make array A into P is same no matter what typewriter Misuki is using. Okay. So what does the problem statement mean, guys? We don't have to minimize the number of operations. We have to minimize the number of carriage return operations, and it should be same for both. Okay. So guys, very, very simple. What does the problem say? Let's have a look. There are two typewriters. Okay. One is on position 1, one is on position n. This typewriter can only move this way. This typewriter can only move this way, right? And now these typewriters can do some things, either move ahead, okay, in their respective direction. Otherwise, do a carriage return. Okay, whatever the spelling of carriage is, I think I'm writing it wrong. It's carriage return. Yes. So what does carriage return do, guys? Let's say this typewriter is over here. If I do a carriage return, it goes back to this particular position. Similarly, if this typewriter is somewhere over here and I do a carriage return, it goes back to this particular position, right? And last but not the least, I can print. And what does this print do? It prints the smallest, okay, smallest positive integer not present in the array. Okay. So what does this problem say, guys? Right? We can do such operations. We need to come up with a permutation that these typewriters will build. Okay. And let's say the minimum number of carriage return operations. Okay. Carriage return operations that typewriter 1 takes is something. It should be equal to the number of carriage return operations typewriter 2 takes, and these are the minimum possible for that particular permutation. Okay. For example, let's take an example, guys. 3, 1, 2, right? Let's take for typewriter 1, which starts over here. Now, guys, before discussing all of this, let's discuss one very simple thing. What is the first number this typewriter can print? Since initially all numbers are -1, what is the first number that is not there in the array? Positive number. It is 1, right? So let's say I print 1. After that, which element will my printer print? It will print 2. Then what will it print, guys? It will print 3. So do you agree that I will be printing this permutation in order? This is a very important observation, guys. What is the observation? That I would be printing the permutation in order. Okay. So first I would print 2, then I would print, first I would print 1, then I would print 2, then I would print 3. So to do this, what will be the operations? First, my typewriter will go here. Okay, then I will print 1. Once I'm done printing 1, I will go and print 2. Now do you see that since I need to print 3, I can't print 4 if there was 4. Since I need to print 3, I need to go back and now basically do a carriage return and then print 3. Now let's see for the other typewriter. Okay. Other typewriter starts here, goes here and prints 1. Okay. Then goes back because you have to do a carriage return, right? I need to print 2, but this can only go this way to the left. So I will have to do a carriage return. I will print 2 and then I will go towards the right 2 moves and then I'll print 3. As you can notice, the number of carriage returns in both operations are 1 and hence this is a valid answer, which is 3, 1, 2. Okay. Now guys, what observations are required to solve this problem? Okay. First is, when do I get a carriage return, right? When do I get a carriage return? right? So I get a carriage return when x plus 1 is behind x. Okay, this is where I get one carriage return. For example, if this is my array and I am this typewriter, so do you see for its direction, x plus 1 is behind x, and hence I would have to take a carriage return and then print it. Similarly, something like 3, 2, 1. In this case, you can see that 1 is behind 2, right? 1 is in front of 2, but 3 is also behind 2. So for this, you will require one carriage return, and this you will require one carriage return. Basically, what I'm trying to say is I will go right, I will print 1. Then I will take a carriage return, go right, and then print 2. Then I'll go back, take a carriage return, and I will print 3. So how many carriage returns are there? There are 2 carriage return in this array. Similarly, you can do it for this array for the other typewriter as well. Now our goal is to make this equal for both the arrays. X plus 1 is behind x. Okay. And this is relative to direction. For this particular typewriter, the other type, this would be a carriage return. Okay. Because this is forward for that typewriter. So guys, the first thing is it always possible? And the answer is actually no. Why is it not possible, guys? Let's say n is equal to 4. In this case, I made 1, 2, okay, at arbitrary positions. Now, you can see that this is already one carriage return for one of the particular typewriters. No matter what I do, one carriage return will go to one of the typewriters always, right? Because either you place it on the left of the last element or right of the last element. So depending upon that, it would go to one of the typewriters. Now, since it goes to one typewriter, we want to make the number of carriage returns equal, right? So now let's say I put 3 here. You can see that this got equalized since one is in the left direction, one is in the right direction. Okay. Now, no matter where I put 4, if I put 4 here, then there would be a carriage return in this direction. But if I put a 4 here, then there would be a carriage return in this direction. No matter what I do, one typewriter is going to get 2 carriage returns and the other one is going to get 1 carriage return. Basically, what I'm trying to say is for any even n, the number of total carriage returns is odd. So there is no way I can split it into 2. Because guys, 1, 2, 3, 4, 5, 6, 7, 8. Okay. How many carriage returns are possible? 1, 2, 3, 4, 5, 6, 7. Basically, for an n, there are n minus 1 carriage returns that you have to split into 2 typewriters. That is why for even n, it is not possible. But for odd n, is it possible? Let's have a look. For n is equal to 5. Simple strategy. I placed 1, 2. So there is 1 carriage return in this direction. I want to nullify it. So I will place a 3 here. Nullify. Okay. Great. Now I'll place a 4 here. You can see that, okay, I've got 1 carriage return in this direction. So for 5, I will place it. And as you can notice, there are 2 in the right direction and 2 in the left direction, right? So one typewriter got 2 carriage returns, second typewriter got 2 carriage returns, and hence this is a valid permutation. So guys, for n is equal to odd, for odd n, you just need to print this particular pattern. You print 1, then 2, 3, 4, 5, 6, 7, and so on. And for even n, you print -1. Okay. I hope this was a very instructive problem. Okay. I kind of proved it to you why the solution works. Okay. So let's have a look at how I implemented this. There are several ways to implement this particular thing right here. But how did I do it? Let's have a look. So if n is even, okay, you can see that I print -1, stating that it is indeed not possible. But for odd n, I take a DQ. Okay, this is a very good trick. I take a DQ and I first push back 1 into it. Then for all I from 1, 2 to n, I push back I if it is even and I push front I if it is odd. Basically what I'm doing is I have a DQ. I initially pushed 1. Then if I is even, I'm iterating from 2, 3 up to 7, right? So if I is even, I'm pushing back. Otherwise, I'm pushing front. Now for 4, I will push back. For 5, I will push front. For 6, I will push back. For 7, I will push front. And this right here is a valid permutation, right? And in the end, I just need to print my DQ. So while DQ is not empty, I print DQ front and then DQ dot pop front. Very simple solution. You can do this using an array as well. This is just how I felt comfortable, right? Nothing to think about it much. Okay, guys. Now we have successfully conquered problem A and B. Let's move on to problem C. So guys, what does problem C say? It's one of my favorite problems. Okay. This is an interactive problem. So what does an interactive problem mean, guys? It means that like you will have to interact with the judge. You will ask it questions, it will give you answers, and based on that answers, you have to decipher whatever the judge is asking you. Okay. So what does guess the tree say, guys? Misuku has chosen a secret tree of n nodes indexed from 1 to n, and it has asked you to guess it by using queries of the following type. It will ask you question mark a comma b. Misuki will tell you which node minimizes distance a comma x minus b comma x, where distance x comma y is the distance between nodes x and y. A task is to find the structure of Misuki's secret tree in at most 15 operations. Okay, so guys, what does this problem say? This problem says that Misuki has a secret tree, okay? And we don't know what this tree is. We can only ask questions of type A and B. And for this, we will be returned a node X such that distance of X comma A minus distance of X comma B, or same thing, right? Other way, is minimum. Okay. So guys, before deciphering how to get this tree, let's see some properties of this distance formula. Okay. Now, before even doing that, one observation that I want you to see is X is on the path between A and B, right? It will lie on the path between them, right, guys? Because we have to minimize something related to distance. So, of course, you would not have something that is not on their path, right? I think this much should be intuitive. Okay. So, if this is A, this is B, X is going to lie somewhere over here only. It could be A and B as well, but let's have a look. So, let's see what we get as X here, right? So what are the distances from A? It is 0, 1, 2, 3, 4. Similarly, from distances B, it is 0, 1, 2, 3, 4. So do you guys see which one minimizes the difference between the distances? You can see that it is this particular node, guys, because 2 minus 2 will give 0. Now, this was for odd path, right? Now let's see for even path. Let's say the distance between them was even, and this is A, this is B. So you can see that this is 0, 1, 2, 3. This is 0, 1, 2, 3. So technically, if you look at the differences, these two nodes, okay, this node and this node both satisfy the constraint. But what does the constraint say, guys? It will return the one closer to A. If there are multiple answers, it will return the one closer to A. So in this case, we would be returned this node. Okay. So guys, do you see anything interesting about this query? Right? I think you should see, right? And the interesting part about this query is that, guys, can you notice that these nodes are the center of paths of A and B? Can you see that, guys? And this will come in very, very handy. These nodes are the centers of the paths. Okay, basically what I'm saying is if the distance is x, these cut them into x by 2 approximately. Okay, in even case it is not true exactly, but yeah. So if this much is clear, our task is to find the tree, right? And for finding the tree, I need to know each edge, yes or no, guys? And how do I find each edge? And how do I find it using the query? If you actually think about it, how will I ever know if two nodes are connected? If A and B are connected, how will I know using my queries? Okay, so the solution is that if I query AB and A is connected to B, I will get returned A. And this is exactly the case when I can say an edge exists between A and B. Yes or no, guys? If A and B are connected through an edge, and I query A, comma B, then I will get A as an answer, and I can say that an edge exists between A and B. Okay. So if this much is clear, what is our goal? Our goal is to fetch all edges, right? And how do I do this? Very simple, guys. First of all, to solve this problem, assume that this tree is rooted at a node. Okay, let's say 1, right? This is rooted at 1. So I will have a tree something like this. Yes or no, guys? Now, all I need to do is for every edge, by some possible means, fetch it. Okay. Now, a special property about a rooted tree, guys. Okay. Initially, the tree was not rooted. Let's say now it is. This connection will always be between a parent and child. And I always know that a node has at most, or exactly apart from the root, okay, a node has exactly one parent, right? So what is our task? For each node, find its parent, right? Find parent for each node. This is our task. So guys, how do you go about solving this? Very simple. Now, for each node, find a parent, right? So let's say this is my tree, okay, which I don't know yet. And I picked a random particular node. Let's say I picked this node. How do I know that this node is the parent of the node I selected? Very simple, guys. Keep in mind that I initially rooted at 1. Let's see what happens when I query 1 and that node x. In that case, this is the path and this is the center. So I will get returned this node. Let's say it is by. Okay, this is by. Then I will query y to x again. Do you see that this is the path now? It got cut in half and now this is the path. And I got returned this node. Let's say this is Z. And now when I query Z and X, do you see that I get returned Z? So right now it might see that it took me the total number of operations itself. But that is not true, guys. We earlier saw, okay, that it gets cut in half. So how many operations will it take till I find this Z? It will take me log 2 of n operations, right? If the path length is n, and every time I am dividing n to approximately its half, okay, then wouldn't it take me about log 2 n operations? And since n is smaller than equal to 1000, log 2 n in this case is around 10. Okay, so do you see, guys, how we can go about solving this problem? For each node, right, you start by querying 1 and I, and till the time you don't get this back, let's say I get x back, then I will just query x and I again, and I will get some other number back. Then I will again query y and I again, till the point till I don't get the same number back. And when I get the same number back, I can say that this node is the parent of I. Okay. If this much is clear, guys, for each node, since I can do it in about 10 operations, right, log 2n, then the total number of operations I will require is log 2n into n. And this worst case is around 10 to 12. Let's consider it's like 12 or 13 or something like that. And n is n. So it took me around 13 n operations to figure out my answer. And my constraint is 15n. So this works pretty well. The time complexity of this is again big O of n log 2n. And let's see the implementation. I hope I was able to clear the solution, how we can solve this particular problem. It's quite intuitive if you look at paths and all of these things, right? So guys, this is my recursive function. Okay. And let's have a look what I'm trying to do. So guys, for every test case, I'm first taking in integer n. Then I'm taking in the parent. I'm having a parent array because I want to store the parents of each node, right? After this, what am I doing? I'm having a recursive function, okay, which does what I exactly said. This is a lambda function, so don't get worried if you don't understand what these are. You can just implement it as a normal recursive function or a while loop. So as I said, guys, I am assuming that 1 is the root. And since 1 is the root, for every node that is not the root, for 2 to n, I am just calling f of 1 comma I. Now, why am I saying f here again? Because when you define a lambda function, you have to pass the function itself because it's recursive, right? So that I can use it again as the variable name. Okay, just avoid it. You can just say that I'm calling f of x comma node for now. Okay, so what am I doing? I'm querying I comma node. Okay, then I'm taking an input. If x is equal to I, then I say that parent of node is equal to I. Otherwise, what do I call? I call f of x comma node. And that is all that I am doing. It's a very simple function. And in the end, how am I printing answer? I am printing out an exclamation mark, and then I'm printing for every node that is not the root. Since one will not have the root, I'm just printing one I, the node itself and its parent. Since I'm doing it n minus one time, I will have n minus one edges, and in the end, I'm printing end. That is more or less it for this solution. I hope you were able to understand it. Moving on to problem D. This is one of my favorite problems because it's a implementation heavy problem. You can use several ways to implement it, right? So let's have a look what this says. You are given an integer sequence A1, A2, AN. Let S be the set of all possible non-empty subsequences of A without duplicate elements. Your goal is to find the longest sequence in S. If there are multiple, find the one that minimizes the lexicographical order after multiplying the terms at odd positions by -1. Okay, so what does the problem statement say, guys? You are given an array of length n, right? And we need to find the longest subsequence, right? Longest subsequence such that it does not contain duplicates, right? It does not contain duplicates. Okay. So guys, since it says that it does not contain duplicates, this should be our first observation of the problem. What is the longest subsequence of an array that does not contain duplicate elements? For example, 2, 3, 5, 7, 1, 1, 2, 3, 5. I can take 2 ones, I can take 3 ones, I can take 7 ones, I can take 5 ones, and I can take 1 ones. Isn't it equal to the number of unique elements in the array? Yes or no, guys? Tell me. The only thing I need to do is find some arrangement of it. So the first part of this problem is very simple. What is the longest subsequence? It's the number of unique elements in the array. Okay. Now, this also should tell us that we will be ordering, we will be finding an ordering, right? Which contains, okay, finding an ordering which contains each unique element once. Now we are given one more condition, right? That we need to find the lexicographically minimum subsequence. Now, what is lexicographically minimum subsequence, guys? In case of 1, 2, 3, 4, and 1, 3, 2, 4, you can see that these two are equal. But when we go at the next index, this is the first index where these are not equal. And since this element is smaller, this array right here is the lexicographically minimum array, right? You cannot form a lexicographical smaller subsequence or sequence for the numbers 1, 2, 3, 4. Now, this is not all that we are given. We are given that find the lexicographically minimum array after multiplying -1 with the odd positions. Okay. So what does the problem say, guys? Or what does this say? It means that let's say you have a subsequence like this. You will be multiplying -1 with the first, third, fifth, and so on positions. And this should be lexicographically minimum. Okay. So guys, if we want a negative number, since all numbers are positive, if we want a negative number to be small, its magnitude, okay, its magnitude should be big. What I'm trying to say is -10 is smaller than -5 as compared to 5, which is smaller than 10. So do you agree that on odd positions, I want as large numbers as possible, because after multiplying them with -1, I will get a really small number. So my goal is to get as large numbers on odd positions as possible, and as small numbers on even positions as possible. Okay. So till now, what did I notice, guys? I noticed that it will contain all unique elements. Okay. And the second thing, I noticed that in the array, in the odd positions, I will try to get as large elements as possible. Okay. And in the even positions, I will try to get as small elements as possible. Right. Okay. So guys, let me take an example and show you the answer for it. So let me take the array 9, 1, 7, 5, 8, 5, 6, 4, 1. Okay. Now guys, since this is a subsequence, okay, if I take the first element to be 7, then all numbers should be after 7, whichever I take, right? Just keep this in mind. Okay. So the first observation is I'm going to take unique elements. Okay. So which are the elements I will have to pick up? I will have to pick up 9. I will have to pick up one of the ones. I will have to pick up the 7. I will have to pick up 5, one of the 5s. I'll have to pick up 8, 6, and 4. Okay. Now my task is to just find an ordering around. Okay. So guys, one more question. Whichever first element I pick up, do you guys agree that all other unique elements, one occurrence, should at least be to the right of it? Yes or no, guys? Let's say I picked up 9. What other elements do I have to absolutely pick up? I have to pick up 1, 7, 5, 8, 6, 4, right? Since all of them are towards the right of 9, this is a valid first element. Similarly, is 1 a valid first element? No, guys. Is 7 a valid first element? No, because 9, which has only one occurrence, is to the left of it. So if I pick these elements as the first element, I would never be able to select 9. If that much is clear, I think we have a very big observation. What is the observation, guys? Let's have a look. So first, I selected 9. Okay. Now, I can remove 9 from the array. This is the first element because I'm forced to have this as my first element. Now for my second element, I want to have it as small as possible. Yes or no, guys? Since it is on an even position, I want to minimize it. Now, guys, not only that, but I want to select such an element such that all other elements occur to the right of it at least once. So which elements are those? Let's have a look. Can I select 1? Yes, because the other elements 7, 5, 8, 6, 4 at least occur once to the right of it. Similarly, can I select 7? Yes, I can select 7 because 5, 8, 6, 4, 1 occur to the right of it. So I have two options for it. I cannot select 5 because 7 will be for the left of it. So since I have two options and I want to select as small element as possible, which one would I pick up? I would pick up 1, right? Okay. So, okay, I selected 1 and now I can just erase it from the array because I would be selecting each number only once. So once I have done this, I can just remove 1 from the array. So now the remaining array is this, and I just need a way to find the next possible element. So the next possible element which I'm forced to take is 7 because all elements are to the right of it. I cannot select any other elements such that all other elements are to the right of it. So I will select 7. I will delete 7 from the array. Okay. Now you can see for the fourth element, I have options 5 and 8. Because even if I take 8, one occurrence of 5 is to the right of it. So I have 5 and 8. I would choose to pick 5 because I want this position to be as small as possible. So it would be 9175, and then I would delete both fives. So for the next position, I have only option 8. So I would select 8 and 6 and 4. So I hope you can see how the answer is 9175,864, which is indeed this answer here. This is basically all that we have to implement, because this would be -9, -7, -8, and -4. And this is the lexicographically smallest. And what I just told you all in words is exactly what we have to implement in code. So what do we have to implement, guys? First, for odd and even position, we'll have to handle it, right? And what is our basic strategy? Our basic strategy is that we are given an array. First, we need to find such a prefix, okay, such that all elements here, okay, if you see all elements to the right of it, it would contain all remaining elements that I have not taken. For example, 2, 3, 1, 2, 3, 3, 1. If you look at this, okay, you can see this split right here. If I select this 2, I can still select the remaining 3 and 1. Okay. Similarly, if I select 1, I can still select the remaining 2 and 3. And similarly for 3, I can select 1 and 2. So this partition is what we have to find first. Okay. And let's see how we can actually find it. Right. So guys, we want to see how many unique elements are towards its right. Okay. So we can just form a suffix array. Okay, not the string algorithm one, just a suffix array, which for every I contains how many unique elements are there in that suffix. And this can be done using a map. Okay. If I show you the initial array, okay, which is something 7 1 6 8 1 5 7 7 9 4. Okay, let's say this is my array. How many unique elements are there in this suffix? 1. How many are there? 2, 2, 2. Sorry, 3, 3, 4, 5, 6, 7, 7, and 7. Since 7 has already appeared here, it won't be counted right now. Similarly, 1 has been here, so it won't be counted. And all other elements are unique. So guys, if you notice, the first partition that we would be making is here, right? Basically, if I select any number from this particular 3 positions, like from position 1, 0, 1, and 2, I can still select the remaining numbers on the right. Yes or no, guys? Because since suffix contains several elements, I can say that if I remove this, all remaining elements would still be there on the right. Now, what did we learn, guys? That on odd positions, we have to maximize, on even positions, we have to minimize. So out of these elements, we would be picking up 7. Okay. And then we will print 7. Now, this is not the only thing we have to get done. We also have to delete 7 from our array. And if you notice, this array changes after we delete 7. After you delete this 7, it does not change. But after you delete these 7s, let's see how the array changes. This won't be as it is. This would be 3, 4, 5, 6, 6. Do you see, guys? All elements in this range reduced by 1. Yes or no, guys? What I'm trying to say is, you saw the last occurrence of 7 and you saw the first occurrence of 7. All elements in between them, whatever were there in my suffix array, reduced by 1. Okay. And now I have successfully found my second partition as well. My second partition is again till here, because no matter if I take 1 or 6, all elements that I can take, unique elements, are to the right of it. So I have to take minimum. So I would take 1, right? Now I would delete this one. So I'm deleting this one from here, deleting this one from here. So my remaining array is 68594. Let me just write that down. 68594. This is all 1, 2, 3, 4, 5. So my array indeed would be 71685 Okay. I'm not going into much of details for the other part, because I think now it should be obvious that all other elements occur exactly once. So now how will we go about implementing this, right? Okay. So first thing that you notice, guys, that when you have an array, you will have a suffix array. So you will need to compute this suffix array. I think this is the easy part. This can be done with a map. Okay. This suffix array implementation. Let me show you my code. It is not the cleanest code in the world, but yes, it is very instructive. Okay. So I have my suffix array, which is here in unique. Okay. So I am iterating back from n-1 to 0. Also, I am trying to find out the last occurrence of a number, because whenever we choose a number to be in my final array, I would need to subtract the entire suffix array from the position that I chose up to the last occurrence of that number. The suffix array will reduce by 1. I hope that much you guys were able to notice. So that is why I'm doing two things. I'm storing the last occurrence of each element, and also I am making my suffix array. I'm iterating backwards, and in my unique array, I am storing the number of unique elements for that particular suffix. Okay. So guys, if this much is done, how to move ahead? Now, another thing that you might have noticed, the partitions are always prefixes. Okay. And the first element is always there. So what do? You can just find what is the number of unique elements over here, or basically what is the value at suffix of I. And then you can just do j++ till the time this value is there in the other values of suffixes as well. It's just a 2-pointer, right? I'll get to what I'm doing here, but basically this is just 2-pointer. Okay. Then you will hit a wall. You can maintain either a multiset or a segment tree to query the max and min in this range. Okay, guys, this is something that you could do, right? I used a segment tree, but I will suggest that for simplicity purposes, you can use a multiset. Because we are iterating over elements, we would be maintaining the maximum and minimum easily using a multiset or a set, right? So you reach till the end, right? And depending whether it's odd position or even position, you found out that, okay, this is, I need to I need to place the maximum possible here or minimum possible here. You found out using a segment tree or using your multiset. How did I implement it using my segment tree? I am maintaining max. Basically, when it's even position, I need to keep, basically when it's odd position, right? I'm using 0 based indexing right here. Index is initially 0. But if you see that when I'm at an odd position, basically the first position, third position, fifth position, I need to have maximum possible elements. So I am maintaining a segment tree, which gives me the range max. And since I know which range I am querying, I am just ignore this for a moment, but I am querying the max in that range, and then I'm pushing it back into my answer. Okay. Now, guys, I have, let's say I found that this is my maximum. Okay, this is my maximum element. This maximum element occurs here also and here also. Do you guys agree for this entire range of elements, this suffix would get subtracted by 1? Because once you delete these elements, because you no longer need them, the number of unique elements in this range for the suffix would go down by 1. So you need to somehow maintain this as well. You can either do this using lazy propagation over a segment tree, or you could use prefix sum to do this. How can you use prefix sum to do this, guys? Very simple. Let's say you chose this particular element, right? Do you agree the next element you would choose is to the right of this? So what can I do, guys? I can maintain a prefix sum array. Okay. I can put a +1 here. And then let's say this is my last occurrence. So I can put a -1 here. And when I make the prefix sum over this, I can make the prefix sum iteratively, but you can see that +1 goes here, +1 goes here, +1 goes here, +1 goes here, and then this becomes 0. So this is the difference array or prefix sum technique we would be using to subtract the values from our suffix array, right? You can do this using a lazy seg tree as well, but that is complicated. I would suggest you use a prefix sum, right? Now, how can you maintain the prefix sum, guys? This is exactly how I have done it. I have my J pointer, okay, which gives me which index I have chosen, or basically till where my barrier is. Okay. Now, if J is smaller than equal to the last occurrence of the max element, then you can see that I'm doing prefix of J plus plus, and I'm doing prefix sum of the last occurrence +1 minus minus. Basically, the prefix sum technique to subtract all values by 1. And whatever value is there in prefix sum of I will just subtract that from unique of I. And how am I doing that? I'm doing that here, guys. If J and prefix sum of J is not equal to 0, then I am subtracting unique of J by prefix sum of J. Then I am adding prefix sum of J to prefix sum J plus 1. And then I'm making prefix sum of J equal to 0. Okay. This is a bit complicated, but I think if you think about it, right? If I am iteratively moving ahead, my J, it goes from 0, 1, 2, so on and so forth. Then initially I'm subtracting the value of prefix sum from my suffix array. After that, I am adding the value of my current prefix sum to the next value of prefix sum, and I'm setting my prefix sum to 0. Okay. Guys, after this is done, since I was maintaining a segment tree, okay, I needed to make sure to delete these elements from the array. And what do I mean by that? I mean to say that I am having an array and I have made a segment tree over this, right? Which is giving me max and min. Okay. So let's say this is 5, this is 5, and this is 5. And this is 3, and this is 3. Okay. So if I delete all 5 occurrences and then I query this range, max is also 3, min is also 3, right? So I need a way to do this. So how am I doing this? I'm storing the index of the range's max. And after that, I can just run a while loop. What is my current max? It is 5. then I know which index it is at. I can set it to, let's say, -1 or something like that. Then again, I will query, what is the max in this range? It is 5, right? Again, I will set it to -1, and again, I will set it to -1. So that is exactly what I'm doing in my code. While I have taken the max element, I am updating that max to -1, and then I'm querying the tree again. And I'm doing that till the point I get an element which I have not taken yet, because each element I can take only once. So I'm having a visited array, which tells me which element I have taken and which elements I have not taken yet. So after I get my first element, which I have not taken yet, I mark it, it's visited as 1. I push it back into my answer, and then I do my prefix sum thing. So it's a very simple solution. If you think about it, my implementation is not that great, I agree. So let's hover through the entire solution once. So I'm having an array and I'm having a suffix array. I'm also having a prefix sum array because I need to subtract values from the suffix array. I'm having an answer and I'm having a visited array. This is not required. Okay. I'm having the last occurrence of each element and I'm having a map so that I can maintain my suffix array. Here I'm creating my suffix array, and also I am initiating the occurrence vector, occurrence map, which stores the last occurrence of each element. Right now, here I'm having just a 2-pointer where what am I doing? I'm initially subtracting anything from my suffix element if there is something in the prefix sum. After that, I am increasing the next value of prefix sum by the current value. I'm setting my prefix sum to 0. After that, if I can maintain my, basically, if I can uh, do J++, saying that if it is equal to the number of elements towards the right, I do J++, otherwise I break. Now, the thing is that when I do J++, I reach such a position at the end where it is not possible. So which is the actual range? It is between I to j minus 1. I is initially 0. Okay. So after that, as I explained, if it is odd, I want to query max. If it is even, I want to query min. These codes are exactly the same. The only difference is here I'm getting max, and here I'm getting min. Okay. So after that, once I get my max element in the range which has not been taken, I push it back into my answer. I do my prefix something where between the current index that I have taken up till the last occurrence, I subtract all values of suffix by 1. And after that, I set my I to query to basically the index that I took plus 1, because all elements that I will take after this, right, would be after this particular index. Let's say the current element that I took was at index 2. So since there's a subsequence, all elements that I will take will be after index 2, will be index 3, 4, 5, so on and so forth. And just to hover over my segment T, I have a node which stores min, max, index of min, and index of max. And how am I combining them? Let's So since A is left part, B is right part, if A dot min is smaller than equal to B dot min, then C dot min is A dot min, and C dot IDX min is equal to A dot IDX min. Otherwise, I set it as B. Now I also need to set max and IDX max, so I can just do that easily as well. So that is more or less for these problems. Thanks a lot for joining in. I hope that you guys were able to learn something new. Apart from that, we have amazing sheets as the CP31 sheet by TLE Eliminators, right? So you can definitely check them out. Thanks a lot for watching again. Bye bye, guys. See you next time.